5, we have predict the molecular shape of IF4 using VSEPR theory. And we want to answer all these questions here in order to, after we predict the molecular shape of IF4. So we're going to first, let me just do this actually, give me a second. Alright, we're back. I do apologize for that. Hopefully we'll be able to go on uninterrupted. But like I was saying, we want to predict the molecular shape of IF4 minus. Okay? So in order to do that, as I said, we need to start by drawing our best Lewis structure. So iodine, okay, would be on the 17th column. Same with the fluorine. So we're actually dealing with 7 times 5. So that's a total of 35 electrons plus 1 because of this negative. So we need 36 electrons to account for. So we're going to put the iodine in the center, okay? And then we're going to go ahead and draw the 4 fluorines attached to it, just like that. And now what we want to do is draw out the valence electrons on the fluorines at least, because we know that right now it's sharing 1 of its 7. So it'll be 2, 3, 4, 5, 6, 7, and the same thing, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, and 2, 3, 4, 5, 6, 7. So now we have this, okay? But iodine as well is sharing 4 of its 7. So it would be 5, 6, 7. Now iodine has an unpaired electron. We can actually fix that there we go. Okay, looks like it stabilized a lot better. So like I was saying, iodine has an unpaired electron, but we can actually fix that because, as it said earlier, we have a negative there, meaning we add 1 electron. And there you have it. This should be a Lewis structure, but let's go over a few checks to make sure this is possible. So yes, first of all, iodine definitely has an expanded octet, which is okay. It wants to do that. But let's see now with the rest of them. So fluorine, in order to have a formal charge of 0, likes to be just 3 lone pairs, 1 bond. Every fluorine is doing that. Iodine, funny enough, same thing. 3 lone pairs, 1 bond. But we can actually modify this picture by, in a sense, adding bonds to it to, I guess, get as close to the iodine as possible. So every lone pair can form 2 bonds. 1, 2. I'll be right here, just waiting for it to load up. Okay, there we go. So we have 1, 2 here and 1, 2 here. Okay, that would be what iodine could do as well to still keep the formal charge 0. But what's happening here is that instead of having 5 bonds in 1 lone pair, it has 4 bonds in 2 lone pairs. So it's actually replaced a bond with a lone pair. It's kind of like that, if that makes sense. And when you replace a bond with a lone pair, you take a step in the negative direction. That becomes your -1. which makes sense considering the fact that iodine, well, IF4 is it's an ion. It's an anion, which is one extra electron. That's where the extra electron is. As we just drew out, it's on the iodine, which makes the most sense in this case to actually balance out this molecule. So now that we've actually drawn the Lewis structure, what does the second step state? Count the number of electron groups, bond pairs and lone pairs, with multiple counting as one effective electron groups around the central atom. So the number of electron groups we have here are going to be 1, 2, 3, 4, but then it also says and lone pairs, 5, 6. We have 6 electron groups, okay? And now, to establish electron group arrangement and then answer, from the electron group arrangement, you can determine the hybridization of the central atom to be, in this case, because we have 6 electron groups, it will be hybridization of sp3, that's 4, d2. Reason why, because think of the s as having it as like one coefficient, so it'll be like s1, but we don't really ever say that, it's just the s. That'd be 1, 2, 3. I do apologize for that because I do want to make sure we can follow along. Hopefully you can hear my voice. I'm just waiting for the stream to kick back up. Okay, there we go. We have S as 1, and then we have the P3, which is counts as 3 more, which is we're kind of get to 6, and then D2, which is the last 2. And that would be 6 in total. So that's the hybridization. It would be sp3d2. And that means for this, the electron, I guess the electron hybridization, the shape would be known as, if I remember correctly, for this, it would be octahedral. Okay? That would be the name for it when it has 6 electron groups. Now, it says that the electron group arrangement is not necessarily the same as molecular shape. What is the name of the basis of this, okay? So with that being said, what we have to do here is we have to actually split the electron groups into whether they're lone pairs or actual bonds. In this case, we have 4 bonds, but 2 lone pairs. With this 4-2 split, the name actually is square planar. Let me just pause here, wait for everything to stabilize. There we go. So we have square planar. What does the shape look like? Well, it kind of looks like this. We have the iodine, well, I mean the lone pairs, and it kind of looks like that, where the fluorines are all kind of circling like that. I want the best 3D structure to think of is kind of like that, with an electron on top and the bottom kind of like a line going through it. And if we were to look at it as a plane, it would be like that for like the fluorines and this for the electrons. So there would be electron up top here and down there. This is kind of what it would look like. You can actually refer to our VSEPR sheet here. As you can see, we have for 6, it's known as octahedral, sp3d2, perfect. And we have 4 and 2, square planar, and that's what we're dealing with here. Now they also ask for the ideal bond angles around the central atom, and that would actually be, at least specifically for the other atoms, a 90-degree angle. The electrons are doing such a good job of distributing it is that it's literally flat. So the fluorines now have the space to be evenly spread out from each other, which would be a perfect 90-degree angle. So they're all 90 degrees apart. That would be the best arrangement, okay? And now I'm just reading through. By analyzing repulsive forces, the only bond angles can actually be observed, and to predict if any deviations will occur. There's going to be differences, I guess, where they're saying that the experimental bond angles might be slightly different than what we predict, but in this case, I do anticipate that it's going to be most likely the ideal bond angle of 90 degrees. And then it says, taking the vector sum of the dipoles, we can evaluate the net dipole movement. And for this, as you can see, based on how we've drawn it in several ways, if we have a dipole movement going in every direction, overall we're just going to end up with they all cancel each other out, especially because they're all fluorines, so they're all pulling each other equally. So in this case, funny enough, this would actually be a non-polar molecule. So for this is more of a discussion than an actual question, but with that, I hope you can see how we first went with Lewis structure, and then we broke it down piece by piece so to get the shape, the molecular geometry, the angle differences, and whether it will be polar or non-polar. Let's see what my colleague has to say. Exactly just the shape that we got. Perfect. 36 valence electrons. We do have sp3d2. Awesome. Molecular geometry is square planar, and the bond angles between the axial and equal is 9 degrees, like that. For equatorial atoms, the bond angle is 120 degrees. For that one, doesn't really make much sense. I don't know where they got in their other 120 degrees from, because it should be all 90. Even technically from the lone pairs to the fluorine, it kind of be a 90-degree angle like that. So I'm not sure where the 120 fits in. But is that the VSEPR theory? Let me just read over these. Exactly, they repel each other, and it's like we do want the 90-degree angle. Not sure what they mean by equatorial, because it can't be 120, because then you'd be something like this, and that's not what we have at all. We have 4 of them, so it's definitely all 90s. I'll give them the benefit of the doubt. I think they definitely have a different shape in mind. I can't think of a VSEPR theory that really abides by that, considering that we have all these different shapes and none of them really have a, maybe like the seesaw, but that's not what we're dealing with at all, or even the trigonal bipyramidal. That may be what they're thinking of, which is not the case here. It would actually be give me a quick second. Alright, I do apologize for that. Hopefully it's stabilized more by now for the stream. With that being said though, like I was saying, unless you're thinking about like maybe trigonal bipyramidal, which is not the case at all. That's where I can think of where we have 120 in plane and then 90 above and below, which is also not the case here. So I will still give them the benefit of the doubt here. But I do want to stress that everything should be 90 degrees. I wish I had a picture of the actual molecule rather than just a Lewis structure. But at least let's see what it says about the dipole movement. With this being said, it does say that IF4 is indeed nonpolar, which is exactly what I was looking for. So although the bonds may be polar in itself, because fluorine is quite an electronegative atom and iodine is not that electronegative, so by comparison fluorine would create a polar bond between it. Because they're all polar bonds pulling equally apart as I drew, it would end up being a non-polar molecule. Okay, So that being said, I'm just going to say this is correct, although all angles are 90 degrees. At least from what I can see. Based on every picture I draw, I cannot understand where 120 degrees would fit. Maybe I may be wrong in this case, but at least from my opinion, all we have here, as the name implies, square planar, only 90-degree angles. So now for question number 6.